Hello and welcome to this lecture series on microprocessor and microcontroller. And currently we are studying 8086 microprocessor, and we are in the 16th lecture of the series, and this is the 6th lecture on 8086. So the topic of current video is we have to understand the interrupt structure of 8086, as well as we will be further learning some simple programs. So in that series, simple program, this is the third video. So we will be learning the interrupt structure plus some simple programs, right? So this video is actually out of the sequence video because earlier I have planned only two videos for simple programs, but 8086 has a larger instruction set, so there are obviously some more important points to cover. So to address the need of the hour, we have this simple program 3 video, right? So now, let me first just tell you what we have done in the previous video. In the previous two videos, we have started with simple programs, right? So we have seen how the data can be transferred between the registers. Then we have seen addition of two numbers, which might be kept either in registers or in external memory of this microprocessor, which is 1 megabyte in its extent. And then we have seen conditional and unconditional jump statements. So here, the jump statements are of both types, conditional as well as unconditional. Unconditional means a simple jump, and conditional means jump with respect to some flag registers that we have. Then we saw loops using jump statement. So one usage of jump statement is we can make loops. It's not always necessary that jump statements are used to make loops only. So we could make loops by using jump statement. This is just one application. Then there are certain dedicated commands for using loops, where CX register by default is used as the counter register. So you do not need to decrement it again and again inside the loop. It will be auto decremented. Then we have seen the demonstration of stack, how stack operates in 8086, and how to initialize the stack segment, and stack pointer is used in conjunction with that. So all of that we have seen here. Then we have seen indexing. By indexing, what we mean is there are various ways to access a particular memory location. So here we have seen that BX register and BP register are used as base registers and base pointer register. So with by using those two together with the segment source index and destination index register, there are various ways of accessing a particular memory location. Then in the last video, we saw assembler directives. Assembler directives are not the part of actual machine code. They are actually there to direct the assembler about where to store the data, where to start the addresses from, etc. So in assembler directives context, we have seen programs in two styles. One is COM style, that is .com style, and another is .exe style. So this .com styled programs, they usually have only 64 kilobyte segment available to them, and they treat code segment, data segment, extra segment, and stack segment as the same thing, right? And first 256 locations in hexadecimal, or first 256 location in decimal, or 100 locations in hexadecimal are stored for writing the operating system. So those locations cannot be used, and your program will begin from 100H. That is why org 100H, if it is written in your program, it is a .com based program, and full usage of 8086 can be done in .exe mode, where the data segment, stack segment, extra segment, and code segment are separately defined. So at a point of time, you can have these at max 4 segments which are concurrently running, but inside your program, you can have as many data segments, as many stack segments as you want. But at a point of time, only one of them will be active. So that's what we have seen in exe mode. So now onwards, we will be using only COM mode for programming, because programming in COM and exe mode remains the same. The only point of difference is in exe mode, the segments are to be initialized separately. So if we understand that, we can do it anyway, anytime. So in COM mode, it is easy to write programs. So we will be writing our programs in COM mode now, so that we can focus on the concept that is being told. Otherwise, exe mode is more useful, as we have discussed in the previous lecture. Then we have seen that in 8086, the call instructions are a little bit different from 8085. First of all, there is no conditional call statement. You can only have unconditional call statement and a return statement corresponding with that. Now, when a call instruction is executed, it can be executed either as a near call or as a far call. In near call, what happens is you are making the jump within the segment. You are calling some portion of the code or subroutine from within the segment. However, in the far jump, you can make inter segment jump, or you can use another segment to jump to. So that's what we mean by far jump. And in near call instruction, what happens is you only put the contents of instruction pointer onto the stack. And in far call, you put the contents of instruction pointer as well as the code segment register onto the stack. Right. So that also happens there. Now, if we talk about function calls in COM, we have also seen that. So function calls in COM style have to be only of near call mode, because you only have one segment there which is treated as all of the segments overlapped. So it is the user's responsibility that he should take care of the fact that he is not making a inter segment jump, because that is possible in coding, but user has to take care of the fact that if he is writing a COM style program, then he should not make a far jump, because that would be an intra segment jump, and in COM mode only one segment is there. So that should be kept in mind. Then after that, in today's lecture, we are going to study these four programs. First of all, we will try to define arrays inside this 8086, because most of the times the data that we have in real world is in the form of arrays. So it is important for us to learn how to define arrays in 8086. After that, we will see string printing instruction. You can print strings onto the screen just as you do in C language in 8086. So there is a dedicated set of commands which is available for printing and manipulation of strings. So we will see one simple instruction here which is called as a string printing instruction. And in the section when we will discuss this complete instruction set, we will see all the string manipulation instructions. So this is a little bit more powerful processor as compared to 8085. Here the user interactivity is better, so we will see it in our programs, right? After that, we will also see how to define macros. So we will see what macros are and how to define macros. If you're aware of C language, you might have heard this term macro. So macros are also present in 8086, and we will see how to define them in 8086. And the most important part of today's lecture is we have to see the interrupt structure, and that's very, very important, right? So we will see all this, and so let me just begin by, right? So want to try. So this is a simple code where we are trying to declare simple array, and that array has these details. Syntax to declare an array of 5 elements named num1. The name of array would be num1, and that num1 array will contain 5 elements, right? So 5 elements will be there, and every location is of 1 byte. Every location is a byte. That means there will be 5 elements in the array, and every location is of 1 byte. And uh, the default value that we want to put in that is 88h. I mean, we want to initialize all those 5 elements with 88h, or by default they will be initialized with some garbage value, right? So in place of h, we may use b for binary, d for decimal. So we all know this, right? So this is the purpose of our program. Now let us see how easily it can be done. So this is a program which is written in .com style. So you will definitely see one org 100h statement here, so that your program can start from 100h hexadecimal location in the 64 kilobyte segment that is available in .com style. So org 100h, then now here you are defining the data segment. In these lines, you are defining the data segment. So here you can see that everything else is comment. Only one line has been defined. Num1 is the variable name. DB means define byte. So it will be having a size of 1 byte. And we need 5 such locations. So the number of elements that you want to have in your array is 5. So we need 5 such locations. And DUP means duplicate. You have to duplicate this value 88h in all those 5 locations, right? So this is the syntax of declaring an array. So num1 is the name of complete array. Or in other way, you can also say that num1 is the name of first element of the array, right? It is also there in C language. The name of the array is the name of the first element of the array. So in C language, this thing is the same. So it comes from here only, that num1 is the name of the entire array, or you can alternatively treat it as the name of the first element of the array. And every location is of 1 byte. We have 5 such locations, and every location will be filled with a value of 88 in hexadecimal. And DUP stands for duplicate. So this is what you have defined in your data segment. You have defined only one array in your data segment. Then your code segment starts. Inside your code segment, you have written your main procedure, and this main procedure is ending here. And what you have done here is you have used the command LEA, load effective address in SI of what? Num1 plus 3. So num1 plus 3 location means third location's value address will be loaded in SI, the offset address of third location, because we know that in this memory structure of this 8086 is such that you have to give the base address of the segment, then you have to give the offset address. So this effective address essentially means offset address, which is the 16-bit offset address after the base address. So in SI register, you are trying to load the address of third location, means num1 is the name of the base location, so base location plus 3. So you are trying to load the address of the third location here in the SI register, and at that particular location, through this command move SI in brackets comma 41h, we are trying to transfer a value of 41h to that particular memory location, although it would have been initialized by 88h, but we are trying to transfer a value of 41h there. So, and then you have ended your program. So this is how simple it is. Let us see just by executing this program. So I am emulating this, and let's see what happens here. So this is your org 100h. So if you see, the code segment has base address of 700 and IP has started from 100. So this is the characteristic of a COM mode program, that IP will have the initial address of 0100. So this is the starting location of your code. So first two things, first 2 bytes that you see here are EB and 05. They corresponding to this jump statement, but let us see just by executing this what happens there. So definitely, if you see here, this org 100h dot data means data segment is defined. So in the initial part of your code, you can see that there will be 5 locations which have this 88h. So 1, 2, 3, 4, and 5. So there are 5 locations which are all initialized with this array. And then you have the code for the rest of this thing. You have the hexadecimal equivalent for rest of your code. So let me execute it one by one. So load effective address SI num1 plus 3. So that SI is as of now vacant. When you execute this, you will get 0105. So 0105 is this particular location. And if you see from the beginning, this is the 0th location, first location, second location, and third location. So starting from 0, this is the third location. So this address, offset address, that is 0105, has been loaded into this SI register, and after executing this command, it will be replaced by 41. So you can see that it has been replaced by 41 here. So through this program, we have seen how to define a one-dimensional array inside your 8086 microprocessor. And if you execute this program further, it will return the control to the operating system. So this program has ended. So in this way, you can define your arrays. Now let's move on to the next program. Which is program number 14, and this is used for printing a string. So before discussing this program, let me show you the output of this program. When you will run this program, you will be able to do something like this. On the screen, that is the DOS screen. Which screen are we using? We are using the screen of disk operating system, that is DOS. And here you have you can show this. My name is then ABCD. So this is the string that has been displayed, this that has been defined here, and it will be displayed, right? So let us now discuss this program. Again, this is a .com style program. So let me just mention here, it's a .com style program. So what we are essentially doing here is, we are first of all starting it from org 100h, then we are defining a data segment. So data segment is only this portion of your code. After that, your code segment has begun. So let us see what has been defined in data segment. So you have defined a variable whose name is MSG, and every location of that variable is of 1 byte, right? And what do you have in that variable? You have a string. So string is defined in this way. You define your string in single quotes, and then you write whatever you want, and the string should be terminated in a dollar sign. So this is the syntax to declare a string. Last character must be this dollar sign, right? So this is how a string is defined in 8086, and you can note the uh, correlation with the C language here, the similarity with the C language, how a string is defined in C language. So this is the way a string is defined here, and every location of this string is of 1 byte. Be it this space character or any character, every location is of 1 byte here, and dollar is treated as the string termination character. Then in the code segment, what you have done is you have simply written a program to display the contents of this string onto screen. And what you have done there, code segment has begun, then you have written the main procedure which ends here. Now to be able to display a string onto screen, you have to call an interrupt, right? You have to call an interrupt. Although we haven't yet talked about interrupts, but for this program's sake, let us just discuss one such interrupt. We will be talking about interrupts in great details from a while from this time onwards. But let us say how to display a string in 8086. So to be able to display a string in 8086, there are three mandatory conditions. First is DX register should contain the offset of the string that you want to display. So the string that you want to display has name MSG. MSG must be stored somewhere in the memory. So we need to have the offset address, that is the address after the base address of that particular segment. We need to have that logical address or the base address in this DX register. And the command for doing that is move DX comma offset of MSG. So this offset is a inbuilt assembler directive. So it will give you the base address in this DX register. So this is a mandatory condition. In DX register, you should have the base address of the string to be displayed. After that, AH register must contain 09 value. If you want to display the string, AH register must contain a 09 value. Why is this so? This is the requirement of interrupt 21H. By interrupt 21H statement, you will be able to display your string. But this interrupt 21H will see whether AH has 09 value or not. If AH has 09 value, then interrupt 21H will be displaying this string onto the screen. If it has some other value in AH register, then interrupt 21H will perform some other task, right? So to be able to display anything onto the screen, AH register must have a value of 09 in hexadecimal. So interrupts requirement is this, and interrupt 21H will look for the starting address of this string into this DX register. So you have to move the offset address there, and then your simply program has been ended. So this is how you try to display your string onto the screen. So let us see the step-by-step execution of that. So first of all, DX register is vacant here, and if you want to transfer the offset address, you will just execute this, and you can see that DX register contains 0102. So in this 0700 segment, if you write here 0102 0102 and hit enter, then you will see that the equivalent of string will be stored there, right? Up to the point where you see some characters, this string is stored over there. And after that, from wherever 90 comes, so this is the default location. I mean, this is not the part of the string. So these are all the characters of a string that we have stored, right? So this is where your string is stored, and you can just see, if you want to see the corresponding characters for that string, right? So NAME, right? Then space is there. So you can see that the string was my name is ABCD. So you can see here MY, then space character is SPA, NAME, then SPA again, that is a space. And if you further move downwards, you will be able to see my name is ABCD, and then there is this dollar sign. Dollar sign, it simply means 24. So this is the termination of your string. Whatever is written after that is not the part of the string that we have. So if you again execute a single step, your AH register now contains 09. Again, if you execute a single step, interrupt 21H has been called, and the program has taken the control to the appropriate interrupt service routine, and then your string is displayed onto the screen. So this is how you can display a string onto the screen, right? Now let's move on to the third program. The third program for today is defining a macro. So this is a program for defining a macro. So let me first show you the output of this program, and then we will discuss what is a macro and what is the need of defining a macro. So this program is very simple. If you run it fully, what this program will do is it will display two strings onto the screen. Hello, my name is dot dot dot, and then ABCDXYZ. So this is what it has displayed. So we have already learned a program where we just want to display some string onto the screen. This program is also trying to display two strings onto screen. But in this program, we are making the use of macros. Now, what are macros? So let us see here. Let us explain it through this program. Let us first see the code segment of this program. So in this code segment of the program, you can see that there is this function main procedure. And what I am doing in this main procedure function, I'm simply moving ex at the rate data and ds comma ex. So this is I'm initializing the data segment. This is unnecessary because this is a com style program. So this is not necessary. So let me just run this program without these lines of code and see if it is correct or not. So yeah, it is correct. So these lines are printed by mistake. So you don't have to write that. So inside the main program, if you see, there are only two statements, print str1 and print str2. So now print is not a part of this 8086 instruction set. Then what is it? How does this assembler know what to do when this print str1 command is given? In the data segment, if you will see, this is the data segment. If you see it here, there are two strings only, str1 and str2, defined by it. And first string is hello, my name is dot 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 and abcdxyz. So these two strings are displayed, print str1 and print str2. Now, what is this print function? This is actually not a function. Print here is a macro. And what do we mean by macro? If you see the top portion of this particular code, this is the top portion of the code. And here we have defined a macro. So first of all, what is a macro? Macro is a uh, sub part of code. Macro is a sub part of code, and this is a template. This is a template. So whenever this program will be executed, in place of this print statement, this complete code will be inserted. This complete code will be inserted. So inside the main program, when you have written print, it simply means that you have written this complete portion of the code there, right? So macro is not a function. In functions we can also do the same thing. We can make functions, and we can call the print function inside our program, but function calling requires you to put some cs and ip content onto the stack and so on and so forth. So that is all there. But the thing here is that when a macro is called, you do not put anything onto the stack. You just replace this print statement by these lines of code. So this is just a short piece of code which will be kept at the appropriate places when your program will be executed. So that's what we mean by macros, right? So in this macro, what I have done is I have defined this by using this. This is the name of the macro that I want to use. It can be any name. And then this is keyword macro. And then this is P1. P1 is the argument that we are using in the macro, right? The parameter one that we are passing in this function. Then what we are doing here is simply the code that we have seen for displaying a string. So move dx offset of p1. So whatever p1 string is passed there, you are moving the offset in dx, keeping ah as 9h and calling interrupt 21h. So this is sufficient to display the string onto the screen. But the next line of codes are written because you want to hit enter after that. So this carriage return character can be also typed by interrupt 21h, but for that EH register should have a value of 02 and DL register should have a value of 0T. So a carriage return character enter will be hit after that. And if you want to have a new line after one line is printed, then you have to put DL 0A, and inside AH you should have 02H, and you should have to call interrupt 21H again. So what will happen is it will print one line onto the screen, and after that it will go to the next line for printing the next line by using these two sets of code. So we do not want to type these lines again and again. So that is why we have defined a macro for this. And since this macro is defined, it can be used anyways. Like in this print statement, print str1. So it will call this macro. It's not a function call where you are just putting some uh, return address onto the stack and so on and so forth. So that's not the case here. It is just your a macro which will be taking this code and replacing it here. str1 will replace p1 and the complete operation will be performed with this macro, so on and so forth for str2 also. So this is what happens in this program. So let's see by executing this program step by step. So when now you are going to execute this print str1 statement, uh, this will go to that particular macro, and you can see that that macro has been executed, and only one string has been printed. Hello, my name is dot dot dot, right? And if you further execute it, uh, let's try to execute this again and again. So the macro is getting executed, so no problem there. Yeah, so first string has been completely printed, and next time when you run it, the second string will be just printed after that string, or otherwise, if you we won't have put the carriage return character and the new line character, this ABCDXYZ would have been printed just after this, which is what we do not want. So in C also we have a slash n character, right, for new line thing. So here that thing has been also implemented in this particular macro. So this is how you can implement a macro inside your programs, and it's a very helpful thing. You can design your own programming language by just defining these macros and functions and using them to make your program more readable like this. So now you can get an idea of how a programming language is developed, right? You have these assembly language instructions here, and you can have these macros and functions which will make your program look more neat. And these macros and functions can be a part of other files, and they can be imported, because whenever you type any program in C, the basic that you do is hash include conio.h and stdio.h for console input output and standard input output. So all of those files, they contain code similar to this, right? So this is how macros can be dealt with. Now, coming to the main part of this particular lecture, we are now going to discuss interrupts. And this is a very, very simple program for interrupts. So let me first make some theoretical background for interrupts, and then we will come to this particular program. So in 8086, these are some seven important points that we need to discuss about interrupts. So first, let us discuss these points, and then we will go to the program that we have written. So point number one is, in 8086, interrupts are of two types. One is external interrupt and another is internal interrupt. So we have got two types of interrupts, external and internal interrupts. So external interrupts means interrupts which comes from the external environment to 8086, and they usually come through two pins in 8086, that is NMI, which stands for non-maskable interrupt, and INTR. We have seen these two pins when we discussed the pin diagram of 8086, and these two pins were available for taking interrupts. NMI means non-maskable interrupt and INTR means it's a maskable interrupt which can be masked. So NMI, it is usually associated with some system critical task. For example, if there is some fire inside your system, so through NMI interrupt, you can just shut down your system, etc. So these types of interrupts cannot be masked. However, INTR is a general type of interrupt which can be masked. It is a maskable interrupt, right? So INTR is also a hardware interrupt which is initiated from the external pins of the microprocessor, and but the status of this INTR, it all depends upon the interrupt flag inside your microprocessor. In the flag register, there is a special bit for interrupt flag. So if that interrupt flag bit is 1, then only this INTR's request will be accepted. Or otherwise, if it is not 1, if it is 0, then the request of this INTR will not be accepted. and this INTR is level triggered, right? So why is it level triggered? There are no answers. It comes from the construction of the microprocessor itself. So INTR is level triggered, right? Then there is internal interrupt. Internal interrupts are usually interrupts which are created by the programs that we write. So some of them are divide by zero. We have a command for division in this 8086 instruction set. So sometimes it might happen that you are dividing a number by zero. So if division by zero is happening, then there should be some error message which should flash onto the screen. So for that, we have got this divide by zero interrupt. Then we have got overflow interrupt. We have also seen the overflow flag. So this overflow interrupt can also be there. Then there is this INT interrupt, which is a software interrupt, and we can use to we can use to write our own interrupt functions by using that. So usually INT is associated with this N. We will discuss what this N is shortly, but INT instruction, it is usually associated with numbers from 0 to uh, FF. That means 0 to 255 in decimal or 0 to FF in hexadecimal. So you can type interrupt 1, interrupt 2, interrupt 3, interrupt FF, etc. in your program. So we will come to this shortly. So these are the two kinds of interrupts that are available in 8086. So external interrupts, NMI and INTR, they are all hardware based, and the internal interrupts that you have, which are divide by zero, overflow flag, then this interrupt instruction, they're all software based instructions, right? Point number two is the non-maskable interrupts that you have in this are NMI, which is a hardware interrupt, which is caused from the external pin. We have just discussed that. Then there is this trap interrupt. What is this trap interrupt? Suppose you have written some code inside the microprocessor and you want to execute that code line by line. So you want to go into the debugging mode and you want to execute that code line by line. So for that, you have a trap flag inside 8086 microprocessor, and you can execute your code line by line. So that is also one non-maskable interrupt. If it occurs, it has to be served. So we will talk more about it, where it is stored, how it is executed in a short while. Then divide by zero is also a non-maskable interrupt. If there is some division by zero error, then it has to be flashed onto a screen. You can't stop that error because the user should know that he's making some error in his program. So he will correct his program. So then what do we mean by non-maskable interrupts? Non-maskable interrupts are all independent of interrupt flag. So in the flag register, there is an interrupt flag bit, and these interrupts, if they appear, they do not check the status of that interrupt flag. Apart from these interrupts, whatever interrupts are there, like INTR is there, INTN is there, all of these, they will check the status of this interrupt flag, right? So this is similar to 8085, although in 8085 the external interrupts were a bit more than this NMI and INTR. And one more important point, NMI and INTR, if they are served, I mean NMI will be always served, right? But INTR may or may not be served. So if the interrupt is getting served, it will be indicated on INTA bar pin. So in the pin diagram, we have seen one pin which was INTA bar pin. So if the interrupts are getting served, that pin will be floated as high, right? So that is the interrupt acknowledgement pin. Now let us look something which is called as interrupt vector table. So interrupts in 8086 are little more organized as compared to 8085. So let me just show you the interrupt vector table and let us discuss what is its meaning and why do we want to use it. So wait a minute. So this is my interrupt vector table. And what is this? Uh, the externally interfaced memory, which is at max 1 megabyte in 8086, first 1024 decimal locations are reserved for interrupt vector table. And what is interrupt vector table? As I have just told you, that we have various kinds of interrupts here: NMI, INTR, divide by zero, overflow, INTN. So all of the interrupts that you see here are all vectored. I means whenever one of the interrupts has occurred, it will have its own address where its code will be written. So that address that address is stored in the form of a table, which is called as interrupt vector table. So interrupt vector table is a table which stores the starting address, of every interrupt. So for NMI, there is some address where its code will be written. So that address is kept in this NMI register, right? Similarly, INTR will have certain address. So all of those addresses are kept in this interrupt vector table. And addresses in what form? Addresses will be in the form of CS colon IP, right? Because we know that if we want to execute the interrupts code, then we have to shift our code segment there. So for the time being, if we want to shift the code segment, we have to put the contents of CS as well as IP in the interrupt vector table. So you can see it here in the interrupt vector table. If we talk about, say, type 4 interrupt, what do I mean by type 4 interrupt? If you write in a software program int04, right? So int04 means a type 4 interrupt. So type 4 interrupt will have these two locations. That is, you will have a location for instruction pointer and a location for this code segment. So IP and CS will be stored in that order, not CS and IP, but IP and CS. IP will be stored first, then after CS, and IP will consume 2 bytes. That is why you will see that um, this location that you see here, it's a 2 byte location. It's not a 1 byte location. So IP will consume 2 bytes, and CS will also consume 2 bytes because they both are of 16 bits. So a total of 4 bytes will be consumed by type 4 instruction. Similarly, for type 3 instruction also 4 bytes will be consumed. So every type of interrupt will have 4 bytes which are allocated to it, right? And you can notice here that if you want to calculate the address of this type 4 instruction, what you have to do is you have to multiply 4 by 4, and the hexadecimal equivalent of that will be the beginning address of this particular location, right? Because every interrupt is taking 4 locations. So obviously, if you want to calculate the address of any kind of instruction, you have to multiply 4 to it, and that's how you will be able to know the beginning address of that interrupt vector table, not the interrupt service routine, but the interrupt vector table, right? So here you can also note one point, that interrupts from type 0 to type 4, they are already named. So interrupt type 0 is for divide by 0 error, divide by 0. So this is again a non-maskable interrupt, and the interrupt service routines base address and the instruction pointers address will be stored here. So at this particular address, the program will jump. Means whenever a type 0 interrupt appears or a divide by 0 interrupt appears, it will come to this interrupt vector table. It will look these 4 locations, IP and CS, and at this IP and CS location, it will jump into the external memory, and there the code of servicing this is actually written. And every vendor can actually modify these addresses according to themselves. So code for divide by 0 and this single step interrupt, that means trap instruction, which is type 1 interrupt, and this NMI, which is type 2 interrupt, and type 3, which is for single byte instruction, reserved for INT single byte instruction, and INTO instruction means overflow, if there is a overflow condition. So these are all reserved for those locations. I mean, these locations are reserved for serving those interrupts. After that, all the locations that you get, these are type N type of interrupts. I mean, if you talk about this instruction INT N, then you have got these locations for that, right? So a divide by 0 interrupt is also called as type 0 interrupt. So if you write inside software int00h, then that will mean a divide by 0 interrupt is called from the software, but it will be automatically called when you divide something by 0, and that will be automatically called in this case from the software, but you can manually call it by calling int00h also. So these are reserved. However, rest all are programmable. These are reserved does not mean that you cannot change these addresses. These addresses can be manipulated by you. But first five interrupts starting from 0 to 4 will have this meaning only. The rest of all are programmable by you, and we can just change their address locations and the code that we want to do that. So these are usually programmed by the vendor of your microcomputer machine. So these first five interrupts will be programmed by them, rest all will be left to you. So this is what we mean by interrupt vector table, right? And from 0 to FFH, you can have all these interrupts. So that is why it consumes 1024 location. FF means 256, and 256 interrupts are there. So every interrupt is consuming, 4 bytes. So that is why it is of 1024 byte. So 1024 first locations of your memory are reserved in interrupt vector table. So interrupt is very structured in 8086, right? So now let us see uh, the next important point. So this is what we mean by interrupt vector table. Then point number 4 is contents of IP and CS and program status word are pushed onto stack when we just call an interrupt service routine. So to be able to implement the interrupt, we need to write a function. So that function is called as interrupt service routine, or in short form, it is called as ISR, interrupt service routine. So those when we call that particular function, then the contents of instruction pointer, code segment, and program status word, they are all put onto stack. So instruction pointer is of 2 bytes, code segment is of 2 bytes, and program status word is of 2 bytes. So they this content, complete content, it is put onto the stack, right? So after that, also this interrupt flag is cleared and trap flag is cleared. Means when an interrupt is accepted, it could be a non-maskable interrupt or a maskable interrupt. If it is a non-maskable interrupt, there is no meaning of interrupt flag. But if it is a maskable interrupt, the interrupt flag should have been 1, and in that case only the interrupt is accepted. But if once an interrupt is accepted, then after immediately accepting that, this interrupt flag will be made as 0, right? This is true for all possible interrupts that are there in 8086, and trap flag will also be set to 0. That means they will be cleared. So when one interrupt is getting served, another maskable interrupt request, if it appears, it won't be served. If you want that to happen, you have to manually set this interrupt flag bit as 1 inside your interrupt service routine. So that is also how 8086 operates. Then after that, a return statement from interrupt service routine is not RET, it is IRET, interrupt return. We will not write RET when we write the subroutine for interrupt. We will simply write IRET, right? Then NMI pin should remain high for at least 2 clock cycles to be able to make an interrupt request. So this is some technical specification of 8086, that if you want to make an NMI request from the external pin, then you have to keep this NMI pin high for at least 2 clock cycles or 2 T states, right? So this is requirement of 8086. It is by construction. Then if there are multiple interrupts, I mean, we have 0 to FF, I mean, this much interrupts are possible. So if there are multiple interrupts at a point of time, then some priority is there. I mean, this NMI has got the highest priority, then INTR, and then in internal interrupts, divide by 0 has got the highest priority, then overflow flag, and then these INTN. But suppose if multiple interrupts are occurring at one time, then this programmable interrupt controller is a separate IC which is used for controlling these interrupts, right? So we will talk about this programmable interrupt controller in a separate session when we will study the interfacing devices. So this controls the priority of multiple interrupts if they occur on 8086, right? So these are some important points about how interrupts is handled in 8086. And now let us talk about the program that we have written here, right? So let me just first elaborate the program that we are going to make, although the program is written here, but let me just show you a text file of how we are going to implement this interrupt. So this is our main program, and the main program is very simple. You are moving a value 4455 into BX register. So this is just a dummy statement just to make your program a little more lengthy. Then you are calling this interrupt 22H. What is interrupt 22H? We are going to define what it will do. So we are calling interrupt 22H, and then simply halt statement. So this interrupt 22H is a user defined interrupt, and we can program it in our way. So that's what we are going to do. So first of all, when interrupt 22H will be called, what will happen? This program will see the interrupt vector table, which is in the first 1024 locations. And from there, it will fetch the address of new CS and IP. and that CS and IP address will be copied to our current CSN IP so that our program control can jump to that particular location. So how do we reach to that location in the interrupt vector table? We will multiply 22 by 4 and whatever is the result in hexadecimal. So location in interrupt vector table is equal to 22 into 4 because every interrupt takes 4 bytes in interrupt vector table to store its CSN IP content. So 22 into 4, this multiplication is in hexadecimal and coincidentally it comes out to be 88H, right? In decimal it would have been the same, but in hexadecimal it also comes out to be the same. So this is a hexadecimal multiplication and the result also should be in hexadecimal. So the location would be 0000 colon 00088 because 88 has been the address, and the 0000 because the first 1024 bytes have been reserved for this purpose. So the address of the base address will obviously be 0000. So this is the page 0. We call this as page 0. So on page 0 your interrupt vector table is written. Page 0 is the first 1024 bytes of your externally interfaced memory, and inside that you have to move to an offset of 0088 to be able to access the interrupt 22H new CS and IP. So we have to reach to this particular location, and there we can write our new CS and IP's location. So let us say that we want to write the interrupt service routine at this location 5000 So at this particular location 0000 and 0008, we have to put the contents of this CS and this as IP. So that's what we will be doing. And on doing that, our table will look like this. So this is 0088 location, 0089, 008A, and 008B inside the interrupt vector table. And we want that when the interrupt vector table is looked, this CS and IP content should be there. So first of all, we will write the content of IP, which is 3412. So 3412, and after that 5000. So 00 will be written first and then 50 in the little endian format. I mean, the higher byte will be stored at higher order address and lower byte will be stored at lower order address. So in the interrupt vector table at these locations, this content should be written. Then only your program will be able to jump at this particular location for interrupt 22H, right? So now uh, if we have already set the CS and IP content, now what is the interrupt service routine? So let us say our interrupt service routine is not doing anything special. It is just moving a value of 5678 in this CX register and simply returning from the interrupt service routine by IRET statement. So this is what our interrupt service routine will do. Although interrupts are made for some sensible tasks, but just for the purposes of demonstration, let us assume that this is the work that our interrupt is going to do. So uh, at location of this, I mean, starting from this 5000 the equivalent hexadecimal code for this should be stored. So here 51234, 51235, 51236, and 51237 will contain the hexadecimal code for move CX 5678 and IRET. So move CX is B9, then 5678 when stored in little endian order, it will be 7856, and then for IRET you have this code CF. So that's what we have to set inside this 8086 microprocessor programming, and then we will be able to run our interrupt. So let me just show you the code. I have written the same code here, move BX, 445H, interrupt 22H, and halt, and I am emulating this program. But as of now, the interrupt vector table does not know where to jump if this interrupt 22H is called. So I will refer to the slides that I have made, and I will make these appropriate changes in the memory. So in this memory, in the interrupt vector table, I have to put this content. So let me just bring on this, and at location 0008, 0089, and 8A, I have to put this content, right? So let me just move to page 0, which begins with 0000, and here I should put 88. So I have reached to this interrupt vector table, and starting from this location, let me double click this. Here I have to put 1234. So 34 will be put first, then 34 has been changed here. Then I will put 12 here. So 12 has been put, and then I have to put 5000. So 00 is already there, and here I have to make the change for 50. So 50 has been put here. So interrupt vector table now contains the address from where your interrupt service routine will begin. Now at the location where your interrupt service routine is beginning, let me just move on to that location, 5000 and then 1234. So here if I go, I have to write the hexadecimal equivalent of my interrupt service routine. So the hexadecimal equivalent of my interrupt service routine is simply this: B9, 78, 56, and CF. So um, here I will write B9. This is B9. Then I will write 78. Yeah, 78. Then I will write 56. And then I will write CF. So this is CF. So B9, 78, 56, CF. B9, 78, 56, and CF. Right. So let me just run this code now step by step, because all of the portions of this code have been completed. So this is our code, and we have put the appropriate content into the memory. And let us run it step by step. So when I have run it in single step, you will be able to see that interrupt 22H will be called now. This is called now, and you can see that the program has automatically jumped to 5000 and 1234H after seeing the interrupt vector table, right? So interrupt 22H, what it will do, it will put the content 5678 in this CX register. So let us execute this, and you can see that 5678 has been put into this, and CF means irate statement. So the program will return back the control, and we will move to this halt statement. So if you run this by single step again, you have reached to the halt statement, right? And this way your program has been executed. Now one thing that you should check is, when this program was getting executed, whether the content of CS, IP, and program register have been put onto the stack before the execution of this interrupt 22H command. I'm telling you that it will happen, but you can check it on your own that it will happen. You can go to the stacks location by seeing the stack pointer, which is FFFE as of now, and the stack segment space address is also given. So you can check that whether that 4 bytes of data have been put into that appropriate locations or not. So the contents of CS, IP, as well as PSW. So it will not be 4 bytes. CS will be 2 byte, IP will be 2 byte, and PSW will be again 2 byte. So that much content, whether it is put onto the stack, you can check it. So this is how interrupts are executed here. You can just write these interrupts by using assembler directives also, but I made this elaborate program just to explain you how things happen inside memory, right? So I guess in this current lecture, we have covered mainly the interrupt thing. We have seen the interrupt vector table and how the interrupts are handled, what type of interrupts are there. So that was the main topic. Apart from that, we have also covered this arrays string printing by using interrupt 21H. And we have also seen how to define macros. So this is, I guess, more or less than it for this particular lecture. I will see you in the next video. Thank you very much.